Oh no! Spaceman Spiff's mothership is disabled. In order to prevent his advanced technology from falling into the wrong hands, he must activate the ship's self-destruct and escape. If Spiff wants the plutonium core of the mothership to detonate the moment he reaches a minimum safe distance of 5,600 meters, and his escape craft, pictured here, launches from the hatch at a speed of 77 meters per second and begins immediately accelerating away at a steady, that means constant, 38 meters per second squared, how many seconds should he put on the self-destruct countdown timer? All right, we have two important events here. We start always by drawing a picture. If he's heading off in a straight line, our first moment is when he launches from the hatch. That's event 1. We're free to call that a position of 0. And moment 2, when he reaches 5,600 meters, the minimum safe distance, and the ship detonates. We call that event 2. We want to know how much time passed between, how much time it takes him to get to here, so he knows, so that we can make the ship detonate at that moment. Okay, of course, we will be using the guess procedure to solve this problem. Let's identify our givens and unknowns. Okay, we know his initial velocity at this moment. We know that his acceleration during this entire period is a constant 38 meters per second squared. That's what's going to allow us to use our constant acceleration equations. We're free to say that this is a position of 0, and we can start the clock there, make that a time of 0 as well. We know where his position at event 2, and then therefore the displacement between events 1 and 2. What we don't know is what his speed will be, what his velocity will be when he reaches event 2, and we don't know how long it will take him to get there. That's what we want to find out so that we can make the ship detonate when he reaches this point. Okay. In order to figure out which equation we use, we look at our set of constant acceleration equations and check. Do we know delta V? No, because we don't know the final velocity. But we know the acceleration, but we don't know the change in time because we don't know how long it takes. So we cannot use this equation. There are two unknowns in it. How about this one? Delta x? Yes, we know delta x. Do we know his initial velocity? Yes, we do. Do we know delta t? No. We know the acceleration, however, but we don't know delta t. We don't. All right, so this equation has just one unknown. We can solve that one. Let's check the last one just to be sure. Do we know the change in the velocities? No, because we don't know the final velocity. Do we know the acceleration? Yes. And we know delta x? Yes. Okay, so we could solve this one too. So between these two, which one do we want to solve? Think, what are we interested in finding? Well, we want to know how much time it's going to take him to reach the minimum safe distance. So we want to solve for the time. So we're going to use this equation right here, the second one. All right, so there's our constant acceleration equation. We want to solve it for delta t. We want to get delta t all together. So I'm going to subtract delta x, the displacement from both sides. And rearranging, I arrive at this. Now we have an issue because we've got a delta t squared right there and a delta t right there. We can't get delta t by itself because this is a quadratic equation. Let's proceed to go ahead and substitute our values in at this point and then talk about solving that quadratic. Okay, so 1/2, substitute in the acceleration, substitute in the velocity, and substitute in the displacement. Simplify these terms, and I'm going to drop the units for the time being while we do the math part to solve it. So we end up with 19 delta t squared, 77 delta t minus 5,600 equals 0. This has the form of a quadratic equation. As a reminder, quadratic equation is always something that looks like ax squared plus bx plus c, where this x is your unknown and a, b, and c are known to you. The solution of any quadratic equation comes from the quadratic formula here. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we know a, b, and c, we can solve for x. Plus or minus here tells us we might get two possible solutions for x, and we will have to decide between them which one logically makes sense for our scenario. All right, so using our quadratic formula, we have our unknown delta t is negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. All right, if we simplify what's under the radical here, square root sign is also called the radical, that comes out to 656.9. So now we're looking at delta t is negative 77 plus or minus 656.9 over 38. So which is it, the plus solution or the minus solution? Well, if we took 77 minus 656.9, we would get a negative number here. Our time interval would be negative, which doesn't make any sense. Our time interval has to be positive. We're going forward in time. Event 2 comes after event 1. Therefore, delta t must be greater than 0. We can't be going backwards in time when we're going from event 1 to event 2. So we have to pick the plus solution here. We have to take negative 77 plus 656.9 over 38. And when we do that, we get about 15.26, rounding to our two significant figures, about 15 seconds. To be safe, we should probably tell Spaceman Spiff to put about a little more than 15, maybe 16 seconds on his timer, so he doesn't get swallowed in the cloud of fire and debris. He escapes.